This is Chris Benson with Science Moab, and today we're going to be talking about the basic geological story of the Moab area and give you some tips on how to explain the sites and sort of the background on some of Moab's iconic physical features. So this is important because we can communicate Moab's geological history, we can place people in time and place, and explain how learning about the past can help us understand the future. And the way you're going to know that you learned it is you can respond to some basic questions and get some practice explaining some of these concepts. So first off, what do we see out there? What are some observations that visitors and locals alike tend to make? People come here and ask questions like, why are the rocks red, or why are they green? They might ask, was this area under an ocean? Sometimes people wonder, are the La Salles an old volcano? They might wonder about those evaporation ponds. What are those for? Of course, they might wonder, is Moab radioactive? They also might ask you about the black streaks on the rocks. They might even ask you if Canyonlands is evidence of a great flood. They might see that climate has been recorded in the different rock layers and say that if climate is always changing, why should we worry so much? They might ask about different drilling rigs up by Dead Horse Point, or they might just want to be looking for some petrified wood or some dinosaur fossils. So hopefully today, the background we're going to give you is going to help you answer some of those questions. And let's face it, Moab's geology is a large part of what brings people here. Initially, natural resources like oil, uranium, and potash attracted prospectors. More recently, though, the exceptional physical features, arches of Canyonlands have really become a world-class tourism destination. And at the core of this activity is the geologic processes that have made Moab unique and shaped its economy for at least the last 100 years. And having a grasp of this geology can help in the following ways. Visitors' experience will be greatly enriched by having a basic understanding of the story of the landscape. If you understand geology, you have a better understanding of where to find certain types of terrain, good for hiking, biking, climbing, where rapids tend to form, etc., etc. Of course, geologic patterns drive topography and landscape scale features, which then set the stage for soil, plants, and animals. Understanding the nature of certain natural resources like potash and uranium, and natural gas and oil can help all of us have a more informed understanding of where in the landscape certain environmental challenges may occur. Also, practical things like, do you build your house on an old uranium mine? Or where does your drinking water come from? Understanding past environments can help contextualize the recent, rapid, human-caused climate change. We can see in the rock record that Earth is always changing, but these changes can take hundreds of thousands, if not millions of years. The rate of change is important. So the way we're going to do this is we're going to go through the layers and talk about how they formed and where you can see them, and then we'll dive down into the modern topography and talk a lot about erosion. But before that, we have to do a quick lesson on sedimentary rocks, the rock cycle, as well as a deep dive into geologic time. Hang on and stay tuned. First off, we should say that we offer this explanation through the scientific lens of observation, evidence, and logic. There are other ways of knowing, such as origin stories, creation myths, etc. And I don't mean to be disrespectful or all-knowing. Geology can answer how, but not why things came to be. And I found that that's important to keep in mind when addressing diverse audiences. So let's jump into geologic time. Moab's rock layers roughly begin where the Grand Canyon's rock layers leave off. There are older rocks here deep below the surface, but we're going to concentrate on the rocks that we can see. The oldest rocks exposed in the Moab area are about 300 million years old. Remember that Earth is about 4.6 billion years old. Geologic time is hard to wrap your head around, but try and think on the scale of millions of years and focus on the sequence of things rather than specific dates. This will really help contextualize our discussion. And it's also worth remembering that 300 million is roughly about 6% of the age of the Earth. Although these rocks are an incredible view into Earth's past, they're still relatively young compared to the rest of the planet. And another way to think of it, the age of the Earth was compressed into a year. Moab's oldest rocks were deposited around early December, and each day of that year would represent about 12.6 million years, and each second would be about 8,500 years. Sedimentary rocks are going to tell stories for those who listen. Most of the rocks around Moab are sedimentary rocks, meaning that they consist of particles of other rocks that have been broken down, then re-cemented together. For example, sandstone, mudstone, conglomerate, limestone, shale. Hopefully, you've heard some of those terms before. Now, the cool thing about sedimentary rocks is that they tell the story of the past environments because these specific rock types form in specific environments. And we can't really prove anything that happened or didn't happen millions of years ago, but we can use logic, observation, and inquiry to interpret these past environments preserved in the rock record. So, for example, sandstone probably deposited in a desert environment, and limestone, you're going to need some kind of shallow marine environment. One overarching theme to help organize your thoughts would be the size of the particles in a sedimentary rock tells us whether it was a high energy environment, so like a large river, a debris flow, a talus field up in the mountains, or maybe a more quiescent environment, like the bottom of a lake or even the bottom of the ocean. In addition to particle size, the color of the rocks can give us broad clues. So red rocks generally deposited in terrestrial or sort of above ground settings that are exposed to air and a little bit of water, so the iron in there tends to rust and turn red. And rocks that are much darker in color, sort of black colored rocks that are sedimentary by nature, tend to have a lot of organic matter in them and often are buried sort of rapidly. So you might see that in a deep sea environment. And one thing to note is geologists use the term formation to describe different chapters, and they're often named for the places where the rocks are best exposed. So we've got the Honaker Trail Formation that was described down on the San Juan River, and the Paradox Formation is well exposed in Paradox Valley over in Colorado, and Chinle Formation is well exposed in the Chinle Valley over in Arizona, so you kind of get the idea. Additionally, geologists are going to use both numerical ages, so for example, 300 million years ago, or MA for short, as well as periods to describe the age of things. So you might know some of these already, for example, the Jurassic, the Triassic, and your timeline in front of you that we're going to keep coming back to has them referenced, and they're very useful for speaking in broad terms about the types of life that existed and what was happening geologically. Before we go any further, I just want to give a shout out to Robert Fillmore, former professor of mine, and this excellent text on the tectonic evolution of eastern Utah and western Colorado. I'm getting a lot of the information from this book, highly recommend it. And then to put all the pieces together, this other book by Ron Blakey and Wayne Rainey is indispensable, Ancient Landscapes of the Colorado Plateau. Most of the paleogeography figures are going to be from these guys, so big shout out to them. Incredibly helpful in putting all this information together. Additionally, we'll be seeing some cool animations from this source as well. The area around Moab has spent the majority of the last 300 million years near or below sea level, which has resulted in a thick sequence of sedimentary rocks. Over this period, the motion of tectonic plates has brought the Moab area northward from the equator and resulted in nearby mountain building, also known as orogeny, both to the east and to the west, which had a profound impact on the local environments and the types of rocks that were deposited. Initially, during the Pennsylvanian period, the ancestral rockies were rising to the east, while a shallow sea and restricted basin covered Moab. Large rivers carried sediment from the mountains towards the shallow sea, which periodically evaporated and left behind thick salt deposits, as well as limestone. Subsequently, in the Permian period, the sea retreated and dunes, rivers, and a dynamic coastline characterized the area. Later, in the Triassic, about 250 million years ago, a different mountain building event, the Sonoma orogeny, occurred along modern-day Arizona and Nevada when an island arc slammed into the western coast of North America, leading to the formation of mountains and volcanoes that spewed voluminous eruptions of volcanic ash. These mountains depressed adjacent lands and resulted in a large coastal plain and shallow marine setting near Moab. Later, the climate became more humid, leading to lakes and rivers carrying sediment to the northwest. About 150 million years ago, during the early Jurassic, Moab was slowly drifting north from the equator and was located in the middle of one of the largest desert dune fields to ever exist on Earth. The climate eased then in the late Jurassic, and rivers and lakes once again returned, this time flowing predominantly to the east, and dinosaurs flourished. Subsequently, in the Cretaceous, global climate warmed and a much larger mountain range began to build to the west, the severe orogeny, which shed abundant sediments through rivers and swamps into a deeper ocean, which covered the Moab area with thick, black, organic-rich mud. Sea level fluctuated, but finally retreated as the dinosaurs, along with about 50% of life on Earth, were wiped out by an asteroid. Shortly after this, about 65 million years ago, the modern Rockies rose up and the Colorado Plateau was uplifted over a mile above sea level. Large lakes formed in northern Utah and western Colorado. About 30 million years ago, the crust in western North America began to pull apart and plumes of hot magma intruded into the rock layers of the Colorado Plateau. Over the last several million years, global ice ages have helped erode the spectacular canyons and mesas we see today. Okay, cool. Let's go into a little bit more detail and slow things down. So take a look at your stratigraphic column and really focus in on the different rock layers. So about 300 million years ago, during the Pennsylvanian period, the continents were slammed together into a supercontinent called Pangaea. And again, present-day Moab was located near the equator and located in a restricted basin near sea level on the margin of this large continent. There was a mountain range to the east known as the Ancestral Rockies. Some of the evidence we can actually see in Westwater Canyon as you're floating through, you go through this very dark rock that's completely different than anything you see in Moab. This is basically known as basement rock, and it's been uplifted from many kilometers below the surface of the earth. So this represents essentially the core of the mountain range, and specifically this would be part of the Uncompahgre uplift of the Ancestral Rockies about 300 million years ago. Now, sea levels fluctuated due to glacial cycles, as there was a large landmass at the South Pole. When sea levels were high, the Paradox Basin would basically be inundated with seawater, and then when sea levels dropped, the restricted basin would retain that seawater, which over time would evaporate, leaving behind sediment, including several types of evaporite minerals, but essentially you can think of it as salt. And we can see over 30 different cycles of this, including the deposition of potash, shale, limestone, and halite. And over many cycles, these deposits grew to be at least several hundred feet thick, probably more like 1,000 feet thick in places. Now we call this the Paradox Formation, and you can see this rock layer along the margins of Moab Spanish Valley, as well as in the depths of Cataract Canyon, and of course, you guessed it, in Paradox Valley. That's the type locality again for this rock layer. And this is also what's being mined over on Potash Road in those evaporation ponds. And it's useful to us because it contains quite a bit of potassium, and you know that plants need potassium. Additionally, there is some organic matter in the Paradox Formation, and that is the source of petroleum that was being extracted up near Dead Horse Point. And subsequently, sea levels remained high, and some of the limestones of the Honaker Trail Formation was deposited in a shallow but more consistent sea. You can see that down by the San Juan River. And in summary, during the Pennsylvanian period, salt was deposited in a restricted basin as sea levels fluctuated. This basic understanding that there's this salt layer underneath Moab is really key. It's the squishy foundation for understanding Moab's unique geology. So we're going to revisit this later on. So moving on to the Permian period, you can kind of think of it as a bit of a tug-of-war. So after the deposition of the paradox, this tug-of-war between a shallow sea, shifting sand dunes, and large braided streams draining the Ancestral Rockies was sort of ongoing. And you can see these rocks around Moab and Canyonlands National Park as the Cutler Group, which includes the Oregon Rock, Cedar Mesa Sandstone, White Rim Sandstone. And the climate also became much more arid during this time than the previous Pennsylvanian period. So the Cutler Formation is well exposed in the Fisher Towers and on the west side of Highway 191 north of Moab. It records these large rivers and braided streams pouring off the Ancestral Rockies. Now further to the southwest in Canyonlands, the Cedar Mesa Sandstone is going to record dunes adjacent to shoreline, and you've got the Oregon Rock Formation sort of recording these streams intermittently, and the White Rim, as you might know, sort of records these sand dunes, all sort of happening at the same time, mixing and matching. Now, one thing that's kind of cool if you're out there on a White Rim trip and you're just thinking about the end of the Permian period, we estimate that something like 95% of life in the ocean disappeared. It's the biggest mass extinction in Earth's history. So they call it the Great Dying, and you're sort of right at that level when you're on the White Rim, looking out between the White Rim sandstone, which is Permian, and the overlying rocks, which are Triassic. And so some new research and modeling is going to point to global warming, surprise, surprise, which we think was caused by massive volcanic eruptions, which emitted a vast amount of greenhouse gases into the atmosphere, which warmed the ocean, reduced the ocean's ability to contain oxygen, and ultimately suffocated marine life. Now, interestingly, this process is estimated to take something around 15 million years. So in summary, during the Permian, there was this tug of war between a shallow sea, sand dunes, and braided streams that ended with the greatest mass extinction event in Earth's history. So moving on to the Triassic. So we deposited the paradox salts in the Cutler Group below. And during the Triassic period, about 250 million years ago, the supercontinent of Pangaea began to drift apart. But also on the western side of the continental margin here, we had an island arc slamming into western North America, which had a huge effect on the sedimentation and the types of rocks we would later see. Many rocks from this period are red in color. This is due primarily to iron oxidizing, so you can just kind of think of it as rust. And Moab at this time was located on a coastal plain, so sometimes it would be exposed to the air and sometimes it would interact with some shallow marine waters. But this tidal flat environment left behind symmetric ripple marks in the Moenkopi Formation as these low energy rivers drained into the sea to the northwest. You can see these rocks really well on the Moab Daly or the edges of the Moab Spanish Valley, also at the base of Castellan Tower. So these are often some of the first red slope-forming layers you might see underneath striking sandstones. And subsequently, the climate became much more humid, and evidence of abundant lakes and streams was then recorded in the Chinle Formation. These rivers carried sediment from both the ancestral Rockies as well as a mountain range to the southwest near the present-day southern Arizona. So these mountains were similar to the Cascades, and they contained numerous volcanoes, and some geologists were not sure exactly where all the uranium on the Colorado Plateau came from, but some have speculated that volcanic ash from these volcanoes actually was deposited in some of the lakes and rivers and then sort of concentrated, and that leads us to the Chinle Formation being one of the notorious rock formations for uranium in the Colorado Plateau. So in general, when you see colorful rocks, greens, purples, and red, you're probably near a layer that contains uranium, and which is sort of one of two, the other one being the Morrison Formation. So in summary, during the Triassic, Moab was the site of a large tidal flat, and subsequently rivers and lakes resulted in some of the most colorful rocks in the Colorado Plateau, and this is usually where uranium is found. Moving on to the Jurassic period, about 200 million years ago, the climate became hyper-arid, and this turned the Moab area into a vast sea of sand, a bit like the modern Sahara Desert. And we can see this in the Glen Canyon group, which would be the Wingate, Kayenta, and Navajo sandstones. Moab was also slowly migrating northward due to continental drift, and it found itself in a drier latitude. And in fact, the Colorado Plateau was probably the site of one of the largest deserts to have ever existed on Earth. And the sandstone deposits are the evidence which basically stretch from Wyoming down to Arizona. So this sea of sand is the origin of many of the beautiful sandstone monoliths that make Moab so iconic, as well as other spots on the Colorado like Zion and the Vermilion Cliffs. So in addition to it being really pretty, sandstone's important because it's a very good reservoir rock. So in terms of aquifers, as well as other resources like hydrocarbons, kind of packed like a sponge, it can hold a lot of things in it. In summary, the beautiful Jurassic sandstones that we see around Moab and climbers really enjoy climbing on was basically the result of a large dune field and a hyper-arid climate. In contrast, in the late Jurassic, this is really when dinosaurs kind of took off and roamed the earth, and the area around Moab became much more humid, and we see evidence of rivers, lakes, and eventually an encroaching sea, and that's going to summarize the conditions for the next 100 million years or so. So a mountain range to the west called the Severe Orogeny was a source of sediment and high-energy rivers that flowed northeastward. This was a much larger mountain building event, which produced the Morrison Formation. And these colorful rocks that were deposited by rivers and lakes can capture a time when dinosaurs were most abundant on the Moab landscape. We see evidence of dinosaur fossils in rock layers like the Morrison Formation, and just above the Morrison, this very colorful brushy basin member, there's something called the Cedar Mountain Formation, which tends to have quite a few dinosaur fossils, including the Utah raptor, which was discovered near Moab. And so you might confuse these rocks with those of the Triassic because they're very red and very colorful, and they form these slopes. And they are similar in the sense that the humid conditions help create some of the most colorful rocks, and those red and green colors are produced by oxidation of iron and even copper sometimes. And similarly, they also have quite a bit of volcanic ash that was trapped in lake deposits and later concentrated, and this is probably what brought uranium into the Morrison Formation, a similar mechanism to the Chinle. So in summary, during the late Jurassic, Moab's environment became more humid, rivers and lakes provided habitat for dinosaurs, and uranium-bearing volcanic ash became trapped in lakes. Brings us to the Cretaceous period. So big changes were afoot in this area and really worldwide. So we're talking about 145 million years ago to 65 million years ago. And this period lasted about 80 million years. The mountains to the west, the severe erosion continued to rise and shed sediments. Global climate change raised sea levels, and the Moab area was inundated by a sea, which was called the Cretaceous Western Interior Seaway. And this was much deeper than the Paradox Basin back in the Pennsylvanian. And we think that this is mostly caused by an increase in global CO2 levels that were estimated to be somewhere around 1,000 parts per million during a period called the Cretaceous thermal maximum. And you can compare that with 280 parts per million pre-industrial, and currently today around 420 parts per million. So 1,000 parts per million is kind of hard to wrap your head around, but that's why sea level increased so much. Interestingly, this is a time when angiosperms, or flowering plants, developed and appear in the fossil record. And although sea levels were fluctuating, the gray, brown, black rocks of the Mancus Shale record a deep 1 to 2,000 foot, mostly quiescent sea in the Moab area. You can see these rocks out by the airport and along I-70 at the base of the Book Cliffs, and they wrap all the way to Grand Junction. So basically everywhere that contains open badlands with that drab yellow-brown color is likely an outcrop of Mancus Shale. So at times, when sea level lowered a bit, large swamp environments resulted from these east-flowing rivers that reach the sea, and we get some coal deposits. And those coal deposits are mined up near Price, down in Black Mesa, and there's potential for coal extraction from this environment down on the Kaiparowits. So the Mancus Shale is notorious for producing high salinity and sort of complicating agriculture. As you might know, it's pretty awful to drive on when it's wet. Some members of the Mancus might have some shark teeth, which is a fun fossil to find. And really at the end of the Cretaceous, this mass extinction event around 65 million years ago, we think was due to a meteorite impact. And this wiped out the dinosaurs and made room for other forms of life to gradually take over. So in summary, over the course of about 80 million years, Moab was 1 to 2,000 feet deep under a sea with a mountain range to the west, which produced abundant sediment and coal deposits. The dinosaurs, as well as about 50% of life on Earth, went extinct at the Cretaceous Tertiary boundary, or KT boundary. In the Tertiary, you can think of things around Moab as being characterized by big lakes, magma plumes, and of course the uplift of the Rocky Mountains and probably the Colorado Plateau. So at the KT boundary, the modern Rocky Mountains began to rise and the entire region began to uplift, forcing the sea to retreat. This would be the last time that the ocean was on top of the Colorado Plateau. The plateau continued to accumulate sediment up to around 30 million years ago. Most of the rivers were draining internally, leaving thick deposits from rivers and lakes. We see this in the rocks that make up the Book Cliffs, but more specifically the Roan Cliffs, and a good place to see these rocks would be Desolation Canyon or even along I-70 as it parallels the Colorado River. So these large lakes in northern Utah were internally draining. They contain quite a bit of fossils and organic matter that got compressed and transformed into oil shale. And additionally, after these lakes kind of filled up, we had these big plumes of magma that were intruding flat-lying sedimentary rocks, resulting in what we call laccoliths. These granite-like, you can think of it sort of like a diorite of the La Salle, Abajo, Henry, and Sleeping Ute Mountains. And we're not exactly sure how or when the Colorado Plateau was uplifted between the beginning of the Tertiary and present time, but some scientists think it was early Tertiary, some propose it was later. But big picture is large-scale erosion began sometime after 30 million years ago. And the Colorado River in the topography we can easily recognize is probably younger than 5 million years old. So going back to our calendar year analogy, that's something around December 31st, New Year's Eve day, so about midday. And about 2.5 million years ago, very recently, the climate changed drastically with the periodic ice ages, which only ended about 20,000 years ago. And that would only be about 2 seconds before New Year's Eve in the context of our calendar comparison from earlier. So in summary, we had these large lakes. The ocean had gone away at this time. We have some intrusions of this granite-like igneous rock, and then we get erosion starting, which really didn't go into its own until very recently, let's say 5 million years ago. So putting this all together, we're going to use this background information to understand the Moab Spanish Valley, some of the arches that we see in the area, as well as the Sal Mountains. So we got to go back to the salt. What happened to those paradox salts that were deposited about 300 million years ago? So you can imagine with thousands of feet of sediments and rocks piled on top of the salt, things started to get a little squishy. And it turns out the salt doesn't compress very well, and it acts a bit like toothpaste when you place what's called overburden on top of it. So these salts oozed, squished, and flowed upward into the cracks, faults, or other weaknesses. And they actually flowed up into a series of weaknesses in the Earth's crust that were generally aligned northwest, southeast. And as it did so, it warped the overlying rocks into these elongate domes, sort of like if you took a spoon and flipped it upside down. And by the way, these are called anticlines. And you might notice that there's several valleys in southeastern Utah and western Colorado that trend northwest, southeast. And this is probably due to pre-existing faults related to the ancestral Rockies. So how does this actually form the Moab Spanish Valley? Well, first off, isn't it curious that the Colorado River cuts across the Moab Spanish Valley? And why is this valley so much larger than the canyon cut by the Colorado River? And so early explorers noted the same curious topography when they observed the Dolores River cutting across a similar valley in Colorado, naming it the Paradox Valley. And that's also where the Paradox Formation is going to get its name. So what happened is these paradox salts in both instances pushed up into an anticline, sort of a dome, along present-day Moab Spanish Valley, and then over millions of years, the landscape began eroding. When the paradox salts came into contact with groundwater and surface water, these salts were easily dissolved and carried away, leaving an unstable structure, which then collapsed into a large, elongated valley. And this same process is thought to have occurred in several valleys across southeastern Utah and southwestern Colorado. And we're going to call them collapsed salt valley anticlines. For example, Castle Valley, Paradox Valley, Lisbon Valley, just to name a few. Now, this is important because these salt valley anticlines, these collapsed salt valley anticlines, create habitat. And you can imagine if the Moab Valley was a regular stream valley, it would look a lot more like Grandstaff Canyon. So what about those arches, and how do they form? Turns out that Moab and the surrounding area have one of the highest concentrations of arches in the world. And you think this could be related to the whole salt thing? Yes, indeed. As you remember, the salt is going to rise and form these domes, which tends to break the overlying rock and form these joint systems. And you can think of a joint just like a crack, basically, especially at the margin of these salt valley anticlines. And these joints lead to an erosion pattern that subsequently favors formation of arches, especially in these areas where there's a strong over weak type of layering. So we see that a lot in the Entrada and the underlying Dewey Bridge. And some other arch forming locations include some thin seams within the Entrada and the Navajo sandstone, sometimes even the Cedar Mesa sandstone. What about the La Salles? They are formed from a very different kind of rock than most of the sedimentary rocks you see around Moab. Essentially, these are called laccoliths, and they mean that a bit of magma intruded into the crust, uplifted some of the layers, and then erosion has stripped away those softer rocks, leaving this steeper mountain formation underneath, kind of like a rock that might have been stuck in a big block of ice and then the ice melts away. That's how we get a lot of these iconic mountains in southeastern Utah, like the La Salles, Abajo, Henry Mountains, etc.
This is Chris Benson with Science Moab here in the Sal Mountains, checking out some of the geology. Now, one thing a lot of people don't realize is the rocks that make up the Sal Mountains are some of the youngest rocks on the entire Colorado Plateau. This rock cooled from a melt about 30 million years ago. If you pick up a piece of this granite-like rock, you can see some crystals in there. That means that it cooled slowly over thousands, if not millions of years, which requires that it's deep below the surface. So about 30 million years ago, a plume of magma intruded into the Earth's crust and deposited this granite-like rock that now makes up the La Salles. Much, much younger, 10 times younger than the oldest rocks we see in Canyonlands Basin, just behind me there. So another thing that's important to realize is about a mile of rock probably existed on top of the highest peaks in the La Salles. So you can imagine Mount Peel, almost 13,000 feet, would have had another 5,000 feet of rock or so. And that's going to give us a much more accurate understanding of just how much erosion's actually occurred here in the Canyonlands region near Moab, Utah.
We've covered a lot of ground. Hopefully you can review this video and rewind and learn all the details that interest you. But big picture, we talked about the rock layers, the stories that they tell, the environmental changes, some of the big picture stories you might see in the rock layers in and around Moab. We've also given you the background to speak intelligently about how arches form, how the Moab Spanish Valley formed, as well as the significance of the La Sal Mountains and just how young these beautiful canyons really are.